So in this video I'm going to talk to you about the distribution of sample means. As per normal, we've got a little Avonford star, which is always a good starting point. So just pause the video and have a read of that. Now, what you'll notice in here that there's a couple of important points. And the important point is that they've taken hundreds of measurements in the past, and there is a standard deviation of 2.5. And the accepted value is 328 parts per million. Now, what we can do here is make a little bit of assumption. And the assumption that I'm going to make in this case is that as you're doing this, actually you're dealing with data that when you're taking a sample from it, the data itself is normally distributed. So here we're looking at parts per million for pollution, and we've taken a sample of all of those. So if we look at the 328 parts per million carbon dioxide in the air, then what we can do is say, well, hang on a mo, let's have a look at our little sample. Now, we've only got a sample of 10 there, so 336 all the way through to 326 with numbers above and below. Now, if I were to plot this sample, that's an incredibly bad line, but if I were to plot this sample, then what I'd find is that actually I'm going to end up getting a values which kind of, don't always, because nothing in life is necessarily perfect, but kind of look like a bit of a normal distribution curve. Now, we've only done 10 here, but let's say, for example, we did 1,000 samples or 1,000,000 samples. Then what we find is that actually this is what our samples, when plotted on a graph, look like. And so if we say, for example, 328's in the center, and we put 310 at the bottom, and we put 350 at the top, or whatever numbers are halfway in between, so more like 340, I suppose, then what we'd have is we'd have a nice smooth curve which resembled a normal distribution. Now, my diagram's pretty poor, and the diagram is irrelevant in this because the whole point of it is thinking about the discussion of it. So what we have is, in the real world, we have a standard deviation of 2.5 for our normal distribution, and let me just pause. So in the real world we have a mean of 328 and a standard deviation of 2.5. Now, unfortunately, we don't know much about the real world other than that. That's all the information we have, and I don't have all the numbers in here. But what I can do is I can then say, well, hang on, let's take a sample of that. So we're taking a sample of data from the real world, and then we're then going to plot our sample onto, again, another normal curve. And when we plot our sample onto another normal curve, what we'll find is that actually the mean stays exactly the same, but the standard deviation changes. Now, in terms of how the standard deviation changes, I'm going to get another video, do one or find one on the internet, which shows you how you get from this one through to this one. But in essence, what it's going to end up being is 2.5 over the square root of however many we have in our sample. So in this case, we've got a sample of 10, so we've got 2.5 over the square root of 10. Now, we've only got 10 values, which are just up here on the screen, and so I don't necessarily want to look at my actual population, because I might not have data for my entire population. I might have data just for my sample. And so all I do is just ignore this, and I look at the distribution of my sample means. Now, obviously I've used the same curve, but actually it won't look the same because the standard deviation is going to be smaller. So if I were to draw it on here, and let's see if I'll use orange, then what I would end up with is a curve that looked a little more like that. That's not too bad, because with a shorter standard deviation you'll have a thinner spike, and the spike will be taller because the area underneath the curve is 1. And so what you can then use is use this information to then move into your standardized score. And your standardized score is worked out in just the same way. And if you look at example 3.1 and 3.2, you'll see how they're worked out. So in this case, standardized score is my value, x, minus the mean. Now notice the means haven't changed. They stay the same. Divided by the standard deviation. Now the standard deviations have changed. And that's very, very important to recognize. So the standard deviation now is sigma over the square root of n. And so what I end up with is two distributions. I end up with one, the distribution for my population, And so that is the distribution of my individual items. So individual items, i.e. every single reading that I've ever made, or every single particle of air that is ever in there. And what we have is that being normally distributed with a mean of mu and a standard deviation, or a variance rather, of sigma squared. And then I can look at a distribution of my sample means. And the sample means, they're distributed normally, because this is distributed normally, with a mean being the same, but my variance now changes. Now you could write that as sigma squared over n if you wanted. I personally like to do my standard deviation squared. Now, obviously your individual items, well, we've looked at a lot of distributions, Poisson, binomial, normal now, and what we found is that they're not all the same. And when you look at things that are normally distributed, you can apply this. And actually, if you look in Stats 3, I think it's the central limit theorem works where actually your individual items might not be normally distributed. There's another distribution you can use for it. So the sample means here currently work on that.